Okay, so last section we're going to look at this week is 7.4, which is on trig identities. So just a reminder, an identity is a formula that is always true, no matter what you plug in. It's not an equation that's sometimes true, like, let's see if I give you guys an example. Like, this is an equation that is sometimes true. Depends if you pick the right value for x. That's a conditional equation. Okay? That's not a trig equation. That's just an algebra equation. Okay? But that's an equation that could be true if you pick the right value for x. This is an equation. Let's see. If I gave that as a problem in Algebra 1, that's an equation that's called an identity. It's an identity because it is always true. It's not a trig identity, it's just an algebraic identity. That's because if you simplified it, you would get 2x plus 7 on the left and 2x plus 7 on the right. So it's an equation that is true no matter what you plug in. That's what we're going to be looking at today with trig. We're going to come up with equations that are always true no matter what you plug in. So, some of these identities you guys should already be familiar with. I think back in section 6, maybe 6.2, 6.3, no, 6.2, we talked about the reciprocal. That was one category. Those are the ones that look like, let's see, do I already have them? No. I won't write them all, but those are the ones like this. 1 over sine is cosecant. 1 over cosine is secant. 1 over tangent is cotangent. Right? Those were the reciprocal. The second group were the tangent and cotangent. Those are the ones like this. Sine divided by cosine equals tangent, and cosine divided by sine equals cotangent. That was the second group. Now, the third group was the Pythagorean identities. We didn't spend a ton of time on the Pythagorean identities. In fact, we've never used them to do a problem. But today, we will. So, Pythagorean identity looks like this. This is one of them. But all of them are on page 403. What I'll do is, I'm going to put that up real quick, just so we have it in the video. Okay, so those are all the different identities. Okay. All of those are in your notes from an earlier section. Reciprocal ones we've been using right along, because we don't have buttons on the calculator for cosecant, secant, or cotangent. So to do those, you have to flip it, 1 over sine, 1 over cosine. We don't use the tangent and cotangent as much with the calculator, and the Pythagorean ones we haven't really used at all. Okay. I'm pretty sure it was in section 6.2. I had you guys write all those down. So these three groups of identities, the reciprocal, tangent, and cotangent Pythagorean, are called the fundamental trig identities. They're kind of the basic ones that if you're going to memorize some identities, these are the ones that you would know. Let's see, this is 7.4. When we get to 7.5, there's other groups of identities we look at. We look at the sum and difference identities. I think we look at what's called double angle, half angle. There's all kinds of blue categories of identities. Not considered fundamental, they're not as basic as these. But in calculus, usually the way it works is if you look at your book, and you flip over the inside cover or in the back cover or somewhere, all of these are in there. And a ton more. Okay? A ton more. But they're basically just different ways to take something that has trig in it and manipulate it to make it look simpler. Why would you want to manipulate it and make it simpler? Well, in calculus, if you had to take something like that and say find the derivative or integral of it, well, it's kind of complicated. It's two different trig functions multiplied together. Maybe if you simplify that first and then do the calculus stuff after, the calculus stuff wouldn't be as bad because you made it simpler to start with. Right? So that's kind of the point of it. Right? And as far as word problems and applications, we won't we won't get into that. You'll see that if you take calculus. All right, so there's your fundamental identities. I already said that. So there's a few different tricks that you can start off with anytime you're asked to simplify a trig identity. Right? Now, these tricks are just kind of general guidelines. I can't really say, okay, every time you see this, you should just do this, right? It's kind of like doing trig identities. It's kind of like playing a chess game, right? You might have an idea of what you think you're going to do, but then as you start doing the problem, you may have to adjust a little bit because things aren't turning out the way you thought it was going to, right? But one strategy that can be helpful is to change everything in the problem that's not sine and cosine into sine and cosine. Okay, so that's one thing that you can always try. Is change everything to sine and cosine. Okay, so we'll try that on the first one. So everything that you know about arithmetic, you can pretty much apply here. Like if you can do distributive property with arithmetic, you can do distributive property with trig functions. Okay? That problem doesn't have distributive. Okay? It's got fractions. Right? So let's see what happens. Okay, let's start with cotangent. How can you rewrite cotangent so that it's just sines and cosines? Yep. If you were thinking, what about 1 over tangent? Yes, you could, and that might help sometimes. But like 90% of the time, the sine and cosine one is better. So that's cosine divided by sine. Okay, and now the bottom. What about cosecant? Yeah, Zach?
1 divided by sine.
1 divided by sine. Right. Now we have a fraction divided by another fraction. What do you do when you want to divide by a fraction? Multiply by the reciprocal. So keep the top the same. And multiply by the reciprocal of the bottom, which is what?
Sine over 1.
Sine over 1. Now, whenever I get stuck, I just pretend like things are numbers. Right? This is just like having 2/3 times 3 over 1. It's pretty much the same idea. What's going to happen when we multiply here? Yep.
The sine's going to cancel.
The signs are going to cancel out, just like the 3's would cancel out. And all you're left with is what was in the first numerator and the second denominator. Cosine over 1, which is just cosine. Right? And that's an identity. Anytime you take the cotangent and divide by the cosecant, you will always get the cosine. So we took something that had division with 2 trig functions and got rid of the division, turned it into a single trig function. Much, much simpler now. And you have a button for that on the calculator if you had to do more with it. But that's it. That's a trig identity. That would be considered probably that's an easy one. Pretty easy. Questions on that? Okay. Let's try this one. Cosecant times tangent. Okay. Cosecant times tangent. Okay, so start with cosecant. How about, Alex, what could I change cosecant into?
1 over sine.
Yep, you can change that into 1 over sine. And Will, what about tangent?
This.
Sine and cosine. And now we're pretty much at the step we were at in the last problem. You don't have to even divide or flip this time. You just multiply straight across. But Riley, before I multiply, anything I can cancel? Yep. And Derek, what does that leave me with right now?
1 over cosine.
Yep. Now, the tricky thing about a simplify is you don't really know where to stop. Okay? You stop there, is that enough?
No.
Well, I would say if you can write something without a fraction, that's simpler than a fraction. So what is 1 over cosine? secant. So, if you take the cosecant of any angle times the tangent of that angle, that's the same as taking the secant. Okay? And the reason it's an identity is because it's true for any angle. Theta could be 12 degrees. Theta could be 19.6. Theta could be anything. In fact, what you write right here, sometimes you see theta, sometimes you see x. It doesn't matter. Just a variable. So what we end with, it depends on the problem. But what we started with was changing everything to sine and cosine. Okay? But you don't always have to end with sine and cosine. In fact, sometimes you might end up with just a number. Some trig identities simplify to a number, like 2. Something special has to happen to get a number. Okay. Right. So again, that would be considered kind of an easier one. Any questions on that? Okay. Now, what we just did there is it's almost like a proof. We proved that this equals that. Did I use any numbers at all to prove the top box and the bottom box are the same? No. It's not like I said, okay, let's plug in 12, and let's do the cosecant, and then let's do the tangent, and then let's do the secant of 12, and then come out the same. No. You can't prove something is true by plugging in numbers, because just because you prove it's true for 12, how do you know it's true for 12 and a half? How do you know it's true for 13? How do you know it's true for 15? Right? You can't check every single number to see if it works. So that's how you do a proof without numbers. Okay? Just like that. Now, this is kind of the opposite of a proof. It's showing something is not true. Does anyone remember from maybe from geometry? Anytime you want to show something is not true, all you need to do is find one of these. And it shows that it's not true. Anyone know what I'm thinking of? How could you show that that is not true? Like the simplest way. Yeah? Right. If you can find a counterexample, all you have to do is find one time that that doesn't work, and then it's not true. Okay? Because to prove something's not true, that's very easy. Just show that it's not true one time, and you're done. Right? Proving something is true, that's harder. You can't just show it's true one time. You have to do a proof to show that something's true all the time. So let's pick a number for theta, but I'm going to use my calculator to do it. All right, so let's type in 1 plus sine squared. 1 plus sine x squared. And that's all divided by cosine squared. So what I should do is put the numerator in parentheses. There you go. So that way it does the entire numerator first. And divide by cosine squared. All right. So divided by cosine squared. You don't need any parentheses there. Okay. And let's put cosine here. Now, when you plug something in, you want to avoid what I would consider like special things for theta. Don't plug in 0. Okay? Don't plug in 90. Okay? Pick a random angle. Okay? So what would be a random angle in radians we could plug in? 23 radians. All right. So if I plug in 23 radians, y1 is this fraction on the left. y2 is the cosine on the right. Did they come out the same? No. So that's a counterexample. So plugging in 23 radians. Again, it doesn't matter. You basically pick anything. Don't pick anything special. Like I wouldn't do pi. I wouldn't do pi over 2. Just something random. Plugging in 23 gave us, let's see, 6.04 on left-hand side and negative 0.53 on right-hand side. Since these are not equal, this proves what's on the left and what's on the right is not equal. Since these are not equal, this, you could just say this is a counterexample. Counterexample. Now, let's say you pick 0. Let's watch. I don't know what's going to happen, but let's just try it. Well, 0 is a bad one to pick, because if you pick 0, what just happened? They did come out the same. So you look at that and you might think, oh, they're the same, right? But try like, try pi. Okay, well that time you can see they did come out different, 1 and negative 1. So there are points where these come out the same, which means if you graph it, okay, that's what's on the left. It's going to take a little while. It's basically like these U-shaped things. And yes, there are vertical asymptotes there too, because you can divide by 0. And what's happening is on the right, you've got cosine. So there are certain points, if you pick them perfectly, that they are the same. Each one of these maximums. And 0 is the one that I picked. So you just pick any value you want for a counterexample. And that's how you prove something is not true. Not a focus of what we're really going to be doing a lot of today. But it is something you could be asked to do, right? Where that would come in is if you ever had a problem that said prove if possible, right? Before I start trying to prove something, if I don't even know that it's true, the easier thing for me to do is prove that it's false. And then I'm done, okay? So if somebody gives me something and says, prove it if you can, maybe I'm giving you something that you can prove, maybe I'm giving you something you can't prove, and it's too complicated for me to tell. I'll start plugging in a few random numbers. And if it keeps coming out the same on the left and the right every time, and I keep trying random ones, then it's probably something that's provable.
Couldn't you just graph it though?
A graph would give you, yeah, if you graph it
for sure if
and they look the same, then it's probably something you could prove. Then you'd have to go through and do the proof. Where you'd have to be careful graphing is like, let's say I gave you a graph like this. And you look at these two graphs. Right? Now pretend you couldn't see what I typed in. Okay, there's the first one. And now somebody walks in the room right now and they look at that one in red. Like, oh yeah, those must be exactly the same. It's drawing it right on top of it. But if you watch what I typed in, you'd know they're not exactly the same. Okay? One of them was a little different than the other. Does that make sense? So the point is, you can, and it might not be as simple as that. You could type in two things that look almost identical when you graph them, but they're actually not because there's a small difference somehow. But yeah, usually if the graphs look the same, then they're the same.
So you check the table?
Yeah, I would check, for this one, I would check the table, right? And I would say, okay, they're trying to ask me to prove if something's true. Let's type in like 0.2, right? And I can say, oh, wait a minute, no, they might look the same, they're close, but they're not. That one's 0.99, that one's 0.98. There's a counterexample that proves whatever I typed in isn't true. Okay?
So if you do have a counterexample, you would just write it like how you did?
Yes. Yep. Now, the last couple problems before this one, I said simplify. Okay? And then I said simplify. Simplify is a little tricky because you don't always know where to stop. Verify is easier. Verify basically means I'm going to start you off with a problem. I'm going to tell you what the answer is. Just show me how to get the answer. So here's a verify. I'm telling you that if you do and simplify the right-hand side, you will get what's on the left. Just show me how. Show me the steps to take the right-hand side and turn it into the left-hand side. Right? And once you've done that, then you're done. You're not guessing where to stop. You stop when you get that as your answer. Okay? That's verify. So the approach that you usually want to do with a verify is take the more complicated side and simplify. Don't take the simpler side and complicate it. I would not try to take sine and turn it into what's on the right. That's going to be hard. Take what's on the right and try to turn it into what's on the left. Now, you can work with both sides at the same time. I'm not going to do that. Some people like to do that. They do a little bit of work on the left, a little bit of work on the right, till eventually the left and the right come out the same. I'm going to stick with this. I'm only going to work with one side. Right? But the goal is you have an equation, and you have to make what's on one side match exactly what's on the other. So, first trick I gave you guys was to write everything with sines and cosines. Second trick is a common denominator. Okay, so remember, in general, when you're trying to find a common denominator, let's say you had a over b plus c over d. Usually to find a common denominator, you multiply each fraction by the other denominator. So here the common denominator is bd. The way you'd get that is multiply top and bottom by d, and multiply top and bottom by b. Now you'd have dA plus cb all divided by db. But that's the pattern. This fraction got multiplied by that denominator, and then this fraction by that denominator. And that gives you a common denominator. Doesn't matter if it's letters, numbers, or even trig functions. Okay? It's exactly the same process. All right, so this is still a simplify. So it's not a verify yet. And when I look at this one right away, I'm not even thinking common denominator yet because I don't have any fractions. Maybe I will get fractions as I start to do the problem. We'll see what happens. Okay. Anyone have a thought what property I could use here first? Yeah?
Tangent is 1 over 2.
So we could try to start changing sines and cosines, everything to sines and cosines. Or there's another property we can use that we use in math a lot. Yeah?
Distribute.
Right. You're going to have to distribute and change to sines and cosines. What order you do that in, it doesn't really matter. I'm going to distribute first. Sine times cotangent is just sine times cotangent. That's all we can do for now. Plus, what's going to come after that? Sine times tangent. Now, the other thing which, if you haven't noticed yet, you will soon. When you start to simplify it, it usually gets worse before it simplifies. To me, that looks worse now. It's longer, it's got more stuff. But it will simplify. All right, how can we make sine a fraction? Let's just put it over 1. And I did that because I'm about to make cotangent a fraction. What's cotangent? Cosine over sine. Right? So, cosine over sine. Plus, I'm going to do the same thing again. What's tangent? Sine over cosine. Now, when you have multiplication and you have the same thing in the top and the bottom of a fraction, you can cancel like this. 2/3 times 3/5. That's fine. The answer there is 2/5. Now, if you had 2/3 plus 3/5, you cannot cancel across a plus sign, ever. The only way to simplify fractions with addition is to find a common denominator. You can't just go like this and say, oh, the answer is 2/5. No. If you add 2/3 and 3/5, you don't get 2/5. That doesn't work. Okay? So you can only cancel when you have multiplication. So, keeping that in mind, is there anything here that I can cancel out? Yeah?
You can cancel sine.
I can cancel the sine. Now, what about the cosine in the top and the cosine in the bottom?
No.
No, that's across a plus sign. You can't do that. So what we're left with now is cosine over 1 on the left plus sine squared over cosine. Now, we've done the trick of changing everything to sines and cosines. So that's not going to help us anymore. What's the second trick that I just gave you? Common denominator. Okay. What's going to be your common denominator here?
Cosine.
What is it?
Cosine.
Cosine. Okay, you just take the product of the two denominators you have. So you don't have to do anything to the fraction on the right. It already has the denominator you're looking for. What would you multiply top and bottom by on the left?
Cosine.
Cosine. Cosine. Cosine. So what's that going to give me
Cosine squared.
on the left?
Cosine.
Cosine squared. What?
Over cosine.
Yep, so that's all over cosine. And what else?
Plus sine squared.
Plus sine squared. Cosine squared plus sine squared over cosine. So now you've changed the sines and cosines, you found a common denominator. There's something there you have to recognize now. Let's simplify this. What goes to 1?
The top part.
Top part.
Pythagorean identity or whatever.
Yep. Cosine squared plus sine squared. Right there. Sine squared plus cosine squared plus sine squared. Same thing. When you add them together, the identity says you get 1. So that entire numerator turns into 1. If you don't see that, then you are stuck. You're going to be stuck there. Any questions how the top turned into 1? That's a Pythagorean identity. Okay. So anytime you see things that are squared, check those Pythagorean identities. And you might see the Pythagorean identities written different ways. Like, if I wrote this, tan squared equals secant squared minus 1. In that box, those are the exact same thing. All I did was take and move something to the other side. That's not a different identity. It's the same identity rearranged. Any questions on that? Okay, so a lot of times that's how you have to look. This identity wasn't really rearranged a lot. It just had these two things switched. That's fine. That's just the commutative property for addition. Sometimes it's rearranged from side to side too. Okay, so now we're at our last step. What's 1 divided by cosine? Secant. So, compared to what we started with, distributive property with addition, 3 different trig functions, and we finished with just secant. So now if we had to go further with this in calc, it's a lot easier to just work with a single trig function all by itself than to try to work with all that stuff we started with, which could be simplified quite a bit. Right. Questions on that? Right, that's more of like a maybe towards a medium kind of. It's not as easy as the first one, but it's not a super hard one. Okay. All right, so now our first verify. So with verify, start with the side that looks more complicated and try to simplify it. Now, sometimes you may start this process and get stuck and realize, you know what, this is just getting worse and worse and worse. Just start over and try a different approach. Right? If you change to sines and cosines first, maybe try common denominator first instead. Okay, try something else. Okay, so first question I usually ask is which side looks more complicated? The right. So that's the side that we're going to work with, right-hand side. Now, we have to decide what we're going to do. All right, so when I look at that, I look at the top, and to me, there's not really much going on there. It's just a single trig function, secant. Not really going to be able to do a lot with it. But you might be able to do something with the bottom. That's a tangent plus a cotangent. Maybe if we work with that, we can simplify it. So for now, I'm just going to leave secant in the top till I work with what's in the bottom. So I'm going to pretend like this is my whole problem for right now. And just work with that. Yep.
Doesn't that just equal 1?
If it was multiplication, it would. Yeah. Because that's like multiplying two things that are reciprocals. But in this case, you're adding them, so it doesn't come out to 1. But it's a good thought if it worked. So let's keep the top the same. So we've got secant. What about tangent? What can I change that to?
Cosine.
Okay. So sine over cosine. Plus, what about cotangent?
Cosine.
Cosine over sine. Okay, now that I did that in the bottom, I see something else I can do. What can I do now with what's in the bottom?
Common denominator.
Yes, get a common denominator and add those up. So, what is your common denominator going to be? Cosine times sine. Yes. So in the bottom, we're going to have cosine times sine. What would you have to multiply top and bottom by on the left? Sine. Sine, sine. Anytime I get a sine squared and then I look later and I'm going to get a cosine squared, that makes me happy. Because sine squares and cosine squares, usually it's going to simplify. Very nice. So, sine and sine. What would you multiply by on the right? Cosine. And cosine. So you've got the bottom, sine times cosine, or cosine times sine, same thing. What's sine times sine?
Sine squared.
Sine squared. Plus, what's cosine times cosine?
Sine squared.
Cosine squared.
Turns out to be 1.
And that whole thing, what do we know about that from the last problem?
Becomes 1.
That whole thing in red becomes 1. So at this step, I would probably do two things, but I'm just going to change all of that stuff in red to a 1. And I'll write it all again for the next step. So secant over 1 over cosine times sine. Now,
You turn the cosine into 1 over 5.
turn the what into what?
The cosine into 1 over sine, and then turn the sine into sine over 1, and then simplify it.
So you want to change this to something?
Yeah, to sine. Don't
You can. No, that's. Not,
wait, never mind.
And you break that up
You
into
can have a
1 over
secant.
cosine.
Think of it like this. Secant over 1, that's the top. And the bottom is 1 over cosine sine. So you basically have a fraction divided by a fraction.
If you turn secant, then you can.
And we'll probably turn secant into something too. So how would you divide a fraction by a fraction? Multiply by the reciprocal. So if I was doing this at this step, I would probably change secant to something. But we can do that in the next step. Times, what's the reciprocal of 1 over cosine sine? Just cosine sine. Cosine sine. And now, look at secant. There's an identity for secant. Secant is 1 over cosine. Okay, so we're really writing out like every single step here. There's a lot of steps you could have combined. Okay. Secant is 1 over cosine times cosine sine over 1. Now what happens?
Cosine cancel.
Cosines cancel out, the 1's cancel out, and what are you left with?
Sine.
Just sine. Now, we know we're right
Oh, you there?
because we go back up and they said verify that what's on the right equals what's on the left, we just got sine, and that's exactly what we were supposed to get. That's how we know we did it right. So if we were supposed to get sine, we got sine, we're good. Okay. Questions on that? Right? A lot of times, I mean, I kind of make it look easy because I ask you a lot of questions, or I change little things like this to make it look like a fraction over a fraction. Some people, you might get stuck there on the homework because you're like, oh, I just see it like this. I'm not sure what to do. You know, like I have secant in the top and then I have a fraction in the bottom. A lot of times, if I have a fraction in the bottom, I just make the top a fraction as well. Make everything a fraction. All right. So the third trick that can come up when we're doing these is to multiply by the conjugate. So we've done conjugates before. We did them with imaginary numbers. Conjugate is when you change the sign of what's in the middle. Okay? We're not going to have imaginaries. We might have something like 1 minus sign, and the conjugate would be 1 plus sign. Okay? So the conjugate is when you change the sign. Okay. So it's a verify, which is good because we're going to pick a side. Now, which side looks more complicated? This is the same, right? Neither one of them really looks more complicated. Here, very clear. The right-hand side is more complicated. Problem like that, same thing as the one we're going to do. I would say both sides look pretty much the same. And this problem and this problem are almost the exact same thing. You've got a trig function that's the same. One side it's in the top, one side it's in the bottom. Cotangent, cotangent, top, bottom. And then you've got a 1 minus a trig function, and then a 1 plus a trig function. Trig function minus 1, trig function plus 1. It's almost the same thing. So we'll probably just do this one. So let's start with the left-hand side. Go through all the different tricks. Would changing to sines and cosines help you on the left-hand side?
No.
Why? Yeah. It already is sine and cosine. There's nothing there that's not a sine or cosine, so there's nothing to change there. It's already sine and cosine. How about a common denominator from what's on the left? Would that help? Why?
You're not adding anything.
We don't, yeah, to find a common denominator, you have to have two fractions on the same side that are separate with different denominators. On the left-hand side, there's only one fraction. There are no common denominators. There's only one denominator, 1 minus sine, right? So the only trick we have left is to try the conjugate. So sometimes the conjugate's in the bottom, sometimes it's in the top. This one, it's in the bottom. What's the conjugate of 1 minus sine? 1 what?
Plus sign.
Plus sine. So go like this and write 1 plus sine. Notice they're using t now for the variable. It doesn't matter. Now, anytime you have a conjugate, you always want to FOIL it out. So the bottom is a FOIL. The top, leave it alone for now. Because usually when you have conjugates and you FOIL them, it's going to cancel that something that's already in the top anyway. Right? So that's my advice. When you get a problem like this, do out the part that's conjugates first. Don't do anything to the top. Leave it the same for now, because something that's in the top right now is not even going to be there in the next step. So it's a waste of time to distribute out something that's going to cancel. Right? You wouldn't know that unless you've done a lot of these kinds of problems. So that's why I'm telling you. Right? So leave the top the same. If you do it out, it's not a big deal. You're just going to have to undo it in the next step. And as you start doing some of these problems, you may do that. You may do something in one step, and then you may undo it in the next step. Kind of like construction on 290. Same thing. So, cosine, 1 plus sine. Now, FOIL out what's in the bottom. 1 times 1 gives me 1. 1 times positive sine. Sine. 1 times negative sine. That's gone. 1 times positive sine, 1 times negative sine. Cancels. When you have conjugates, the outer and inner don't matter. So the only part of FOIL that you really have to do is the first and the last. So 1 times 1, negative sine times positive sine. Negative sine squared. Now, I told you when you see an exponent of 2, what word should kind of pop into your head? Pythagorean. Yes, Pythagorean. 1 minus sine squared. Let's go back and look at this. Does 1 minus sine squared look like any of the Pythagorean? The first one. Not exactly, but if you move some stuff around, 1 minus sine squared equals what? Cosine squared. So let's do that. 1 minus sine squared is cosine squared. Keep the top the same again. Cosine, 1 plus sine, over cosine squared. If you want to think about that in numbers, that's kind of like having 3 times 1 plus 2 over 3 squared. That's 3 to the first, that's 3 to the second. There's a common factor in the top and the bottom. You could cancel a 3 out from each spot. When you cancel it from here, it's gone. And when you cancel it from here, you're just left with a 3. So, what would happen? What would cancel over here? How many? 1. 1 from the top, 1 from the bottom. And you're left with 1 plus sine over cosine. Look at what you were supposed to get on the right-hand side. 1 plus sine over cosine. Every problem that looks like this is exactly the same. It's pretty much exactly the same setup. So I'm not going to go through the next one, but if you were to do this one, you'd pick a side to start with. It doesn't matter. Start with the left. Multiply top and bottom by cosecant plus 1. When you do it in the top, you're going to get a trig identity, and it's going to cancel something that's in the bottom. And that's going to be the final answer. It's no more or less work if you start with this side either. It wouldn't have made a difference. In that case, you'd multiply top and bottom by cosecant minus 1. FOIL what would be in the bottom, and it will cancel something that's in the top. All right. No, I'm just picking random ones at this point. I don't know. Let's try this one. I gotta remember how to do it. So it's tangent squared minus 1 over secant squared, and that equals tangent x minus cotangent x over tangent x plus cotangent x. So what I'm trying to decide right now is which side I should start with. I'm not sure.
Is that the tangent squared of -1? Or is it supposed to be x?
Tangent squared, yeah, I technically should have an x right there. Yeah. So I know from the Pythagorean identities that 1 plus tangent squared equals secant squared. Now, that's not what I have. I have tangent squared minus 1. So this isn't quite a Pythagorean identity if you look it up again. Okay, it would have to be a plus right there. All right. So, let's, I don't know, you guys pick. What side do you want to start with, left or right? Left? Yeah, let's try right. I'm not sure what to do on the left, other than you could change secant squared to 1 plus tangent squared. I mean, that's factorable. You could factor that as tangent plus 1, tangent minus 1. That's a difference in 2 squares. It's like factoring this. Squared minus 1. Same thing. But I think I'm going to start with the right. Okay, and see what happens. So, what could we do on the right-hand side with all those tangents and cotangents? Yeah, we could change them all to sines and cosines.
Would there be one that's default?
Would there be one like this?
Yeah.
You never know.
Right.
Maybe.
Mm.
So, trying to think of the easiest way to do it. Let's try sines and cosines. I don't. It'll work eventually, but I'm thinking there's got to be a much faster way. So, right hand side. So we got sine over cosine minus cosine over sine. Now, I was kind of tempted to almost leave that because the top on the right had a tangent. The top on the left had a tangent. So they already had something kind of in common. We just messed that up by changing to sines and cosines. Maybe it'll help eventually. The bottom, I definitely want to change to sines and cosines. Okay, because the bottom here has a secant. The bottom here doesn't even have a secant. So we gotta do some work with what's over here to fix that. Okay, the top, I'm not sure that was the right thing to do. We'll see. All right, and in the bottom, it's the same thing with a plus. Sine over cosine plus cosine over sine. Now, I think we've already done this problem right here. Sine over cosine plus cosine over sine. Let me go back for a second. Sine over cosine plus cosine over sine. Okay, so we've done that part. We multiplied and found a common denominator. And we ended up with 1 over cosine sine. Okay. Maybe we should just do it again, so that way you can see how to do it again. But the idea now is in the bottom, find the common denominator. Okay. So would you multiply the fraction on the left by sine? And the one on the right? Cosine. And I'm going to keep the top the same. In fact, I think I'm going to end up changing the top back to what it was. I'm not sure yet. So sine over cosine minus cosine over sine. In fact, sometimes what I do when I'm solving it, if I don't want to keep writing the top over and over, I'll just pretend the top's not even there for now, and I'll just keep doing the bottom. And then when I get the bottom the way I want it, I'll come back to the top. Okay. But I'm afraid if I don't write the top, some people might forget that it was even there. So I'll just keep writing it each time. All right. So we're going to get sine squared. Sine times sine is sine squared. X. Cosine times cosine is cosine squared. And what was my common denominator? Cosine times sine. Or sine times cosine. Same thing. Sine times cosine. Okay, and now what happens to sine squared plus cosine squared? That becomes 1. So if I was doing this, I would probably just erase that step and put a 1. But I know when you're taking notes, it's kind of confusing if I just erase it. So I'll copy it all again. So sine over cosine minus cosine over sine all over 1, and then sine, cosine. Okay, so at this, I think we should put the numerator together and see what happens. Find a common denominator, because I'm kind of stuck on the bottom right now. The bottom is supposed to turn into secant squared. That's not secant squared at the moment. Okay, so let's try putting the top together, and then we'll have a fraction over a fraction. We can try the reciprocal. And then at that point, something just has to happen that's good. Otherwise, we're stuck. All right, so in the top, what's the common denominator there? It's pretty much the same as what's in the bottom. It's cosine times sine again. So I'm just going to add it to the last step. Sine, sine, cosine, cosine. Now, it's not going to be sine squared plus cosine squared. It's going to be sine squared minus cosine squared. So there is no Pythagorean identity there. So sine times sine, sine squared, minus cosine times cosine, over sine cosine. So that's sine cosine. That's the top. And the bottom, I didn't do anything to it in this step. But I'm not going to write it as divided by 1 over sine cosine. Instead, what can I do? Instead of dividing by this, I can, yeah, can multiply by the reciprocal. Now, as I'm going through this, I'm getting a feeling. Okay? I'm getting a feeling I really don't like anything that's happening. I'm not feeling like I'm getting anywhere. I don't think I'm doing anything wrong. I just don't think I'm getting where I need to go. Right? Because I'm getting sines and cosines, and I'm doing a lot of steps, and it's not starting to look like what I want yet. So this is a step where I'd probably say, you know what, I'm going to step back and try something else. Because now these cancel, and you've got sine squared minus cosine squared, which is not tangent squared minus 1 over secant squared. Right? It's probably equivalent, but it's not what they wanted you to get. So I had some work here that I erased. And what I'm going to do is I'm going to undo and see if I had that's not enough work for me to figure out what I did.
That's part of it.
So looking at that work, I'm guessing I did not change to sines and cosines because somehow I did get the answer, but the second to last step had no sines and cosines in it. So let's look at the right-hand side again. So this is what's going to happen to you as you do identities most of the time. Okay, the first ones I made them look pretty easy because I just kind of had an idea what to do. This one I'm kind of stuck at the moment, but I will get unstuck someday. Besides changing to sines and cosines, what else could I try? I could have tried the conjugate, right? And I'm guessing that's probably the way to go here. try the conjugate first. All right. What I'll do is I'll try that, and that's probably going to work. But I'll do that after, and I'll put it as the last problem in the video. So I'm just I'll put the homework up, I'll pause the video, and then if you want to see if the conjugate worked, just look at the video tonight and just skip the whole last 10 minutes because that didn't work. And go right to this and you'll be able to see if it worked. But I think the conjugate's going to work. Okay, so homework tonight on 407. And it's 4 through 8, 11 through 13, 18 to 23, and 25 through 30. And we'll take a look at that tomorrow, and I will figure out this problem. And if you don't watch the video, I'll show you how to do it tomorrow in class. Okay, so I figured out how to do this problem. The key is rather than changing to sines and cosines, which may work somehow eventually, we want to change to tangents. So working with the left-hand side, we're going to keep that as tangent, just make it a fraction, and we're going to write cotangent as 1 over tangent. So start with that. In the bottom, we're going to make it tangent over 1 plus 1 over cotangent. Now, what I want to do with this step is, this should be tangent. What I want to do now is find a common denominator in the top and bottom to write those all as one fraction. So, common denominator in the top is going to be tangent. Common denominator in the bottom is going to be tangent. Now, let's do this out and see what happens. Multiply by tangent over tangent. The other fraction, you don't have to multiply anything by in the top because it already has a denominator of tangent. So in the top, that's tangent times tangent, which is tangent squared. And in the second part, all you have to do is copy down the minus 1 because the minus 1 already had a denominator of tangent. So that's what's in the top. And that's what's in the top here. Okay, bottom. Common denominator, multiply by tangent, multiply by tangent. That gives you tangent times tangent, which is tangent squared. And the plus 1 we can just put because the 1 already had a denominator of tangent. Okay, so now let's rewrite this part. Instead of having a fraction over a fraction, let's write it as multiplied by the reciprocal. So tangent squared minus 1 over tangent times tangent over tangent squared plus 1. Put my x's in there. Okay, tangent in the bottom, tangent in the top. That's gone. Now I have tan squared x minus 1. That's the only thing that's left in the top, and that's exactly what I wanted in the top. Now, the bottom is supposed to be secant squared. Right now in the bottom, I have tangent squared plus 1. But if we go back and look at the identity, I had tangent squared plus 1. Well, tangent squared plus 1 turns into secant squared. So, go back right here. This that I'm underlining turns into secant squared because of that Pythagorean identity. So we end up with tangent squared minus 1 in the top, and we end up with secant squared x in the bottom, and that's exactly what we were supposed to get. So changing to sines and cosines was definitely not the way to go, but changing to tangents and then finding a common denominator, that way worked out here.